Welcome! One of the problems with global warming is trying to tease out the long-term trends from what is basically very noisy data, which has a large number of fluctuations superimposed on it caused by natural cycles in the Earth's climate. I'm going to present to you today a completely new way of looking at these data that teases out those trends very straightforwardly by eliminating fluctuations and noise. What I'm showing you here is the global land and ocean temperature anomalies over the last 140 years. You can see the data is very noisy and there are many short-term fluctuations. There are cooling trends periodically. There are also equivalent warming trends. But it's only when you take a step back and look at the overall picture that you can see long-term trends. For example, in the last 50 years there's been a distinct warming trend. Now mathematically you can determine, based on the level of noise and the size and duration of the fluctuations, that how long it would take to tease out a trend of about the level of warming that we're seeing of about 0.2 degrees centigrade per decade. And that turns out to be at least 20, maybe even as much as 30 years to measure that trend. However, there's a way of short-circuiting that if you know what is causing the fluctuations. We know that one of the major influences on global temperatures is the so-called ENSO cycle, the cycle between La Niñas and El Niños taking place in the Eastern Pacific. La Niña is the cool side of the cycle, shown here with the cool waters off the South American coast, and El Niño is the warm phase of that cycle, shown here on the right. But these maps don't really help us apart from telling us that such a cycle is occurring, so we need some sort of index, some sort of quantitative measurement that will characterize the size and the length of these cycles. One such index is called the Southern Oscillation Index, which is a measure of the pressure difference at sea level between Tahiti, which is there, and Darwin, which is in northern Australia. Now you note that this really deals with just the tropical areas of the planet. There's a new index that is much more comprehensive called the Northern Oscillation Index, or NOI, which is the sea level pressure at the Northern Pacific High, which is up here, and again compared with Darwin. And this is now believed to be a much better indicator of what will change the global climate, in particular global temperatures, and so I'm going to use that quantity from this point onwards. Here we have one of the categories as an example. This one is for NOI less than minus 1.5, i.e. this is a cooling period and a very strong La Niña. So what I've done here is every time I found an NOI that is less than minus 1.5, I've read off the global temperature anomaly at that time and plotted it on this plot over this 70-year period. And as you can see, despite this being a cooling time in the Earth's climate, the overall trend over the years is a warming trend, and this blue dotted line here is a least squares fit to that data, and I've recorded what the slope and the offset is for this, and we could compare each one of the 8 categories that I put together to see what the differences in these trends are. Here we have the results from the 8 categories that I defined earlier. In the blue square we have the La Niñas, A being a very strong La Niña, B being a moderate La Niña, C being a weak La Niña, and D being basically ENSO neutral conditions but with a slight tendency towards the cooling phase. E here is ENSO neutral conditions but favoring slightly El Niño conditions. F is a weak El Niño, G is a moderate El Niño, and H is a strong El Niño. And the remarkable thing about these plots is basically the trend is identical between them, certainly within the uncertainties of the measurements. To avoid confusion, I plotted all 8 trend lines on the same plot and color-coded them accordingly. The blue one at the bottom is the strong La Niña, the brown one at the top is a strong El Niño, and all the others lie in between. And the remarkable thing about this is the trend lines are very similar one with another, and in fact identical within the uncertainties of the measurement of that trend line. So no matter what the conditions are in the Pacific, we're getting basically the same trend in global warming, namely an average of 0.14 degrees centigrade per decade over the last 70 years. Now you could apply this same sort of analysis to any other factors that you can quantify. The level of volcanic activity, for example, or in this case sunspots. However, if you look at this scatter plot of global temperatures against sunspot number, you can see that such an analysis would be futile because there is no pattern here at all. In fact, for any given number of sunspots, there's something like over a degree uncertainty in the temperature that would result. That applies to a very wide range of sunspot numbers. But just to be thorough, I fitted a least squares fit to this data, and you can see it with this black line here, and the slope of that line is 0.0003 degrees centigrade for every sunspot number increase. Now this slope is very uncertain because of all the noise on this data, but let's take that as the typical value, and that enables us to see what the effect of going from solar maximum to solar minimum would be for a typical solar cycle. A typical solar cycle is about 130 in sunspot number, and so you multiply that by 0.0003 and you see that it makes 0.04 degrees centigrade difference in global temperatures. So this is about the effect you would expect if we went from a normal cycle to a Maunder minimum. And so with global warming increasing at a rate of 0.2 degrees centigrade per decade, we would compensate for this fall from a normal cycle to a Maunder minimum in just 2 years of global warming. So this just shows you how insignificant the sun's variability is in affecting our climate. So in conclusion then, we have learned that removing the effects of the Pacific temperature fluctuations produces no effect on the rate of global warming. No matter what value of NOI we chose, we got basically the same rate of warming. On average, that rate was 0.14 degrees centigrade per decade. We found no trend between sunspots and global temperatures. Thus, even the largest solar cycle would produce less than 0.1 degrees centigrade change in global temperatures. And even if we went into a grand solar minimum, a new Maunder minimum, that global temperatures would drop by a mere 0.04 degrees centigrade, which would be compensated for in less than 2 years of normal global warming at its current rate. And the chances of going into a Maunder minimum are 0 to none, and therefore the chances of an ice age are even more remote than that. So until next time, goodbye.